In this audio precision technical training seminar, we're going to talk about LabVIEW drivers for the APx500 series of audio analyzers. We have two LabVIEW drivers for the APx500 series instruments. First is the APx .NET LabVIEW Driver. This provides a LabVIEW interface to almost all of the features available in the APx500 control software. It uses the APx Application Programming Interface, or API, which is based on Microsoft.NET. And it's available for virtually all of the instruments in the APx500 family. Secondly, we have the APx LabVIEW DAQ Driver. This is more of a typical LabVIEW data acquisition driver. It uses a low-level C++ library that controls the interface to the analyzer, and it only works with the APx515 audio analyzer, which is intended for production test. This table shows a comparison of the two LabVIEW drivers. So on the left we have the APx LabVIEW .NET driver. As I mentioned, it requires the APx500 software. The APx LabVIEW DAQ driver on the right is completely independent of the APx500 software. The .NET driver, of course, requires Microsoft.NET, whereas the DAQ driver is based on low-level C++ functions. The .NET driver provides a LabVIEW framework and a wrapper for much of the APx500 API, whereas the DAQ driver is a true instrument driver. The .NET driver is complex in the sense that it's very feature-rich and includes all of the measurements that are available in the APx500 software. The DAQ driver, on the other hand, is very simple. It provides generation and acquisition of waveforms and a few simple audio-based measurements. The .NET driver works with any APx audio analyzer, and the DAQ driver works with the APx515 only. So first let's talk about why people would want to use LabVIEW with our audio analyzers. So many of the things you want to do in audio involve generating and acquiring and analyzing waveforms. And LabVIEW has some very nice features for handling waveforms. There's a built-in waveform data type, which makes it very convenient to work with waveforms. And there are also a series of VIs for processing waveforms, generating waveforms, conditioning them, such as filtering, and working with signal analysis of waveforms. LabVIEW also has some very good connectivity, first of all to other test and measurement instruments through its library of instrument drivers. And it has good connectivity to other programming technologies such as ActiveX, .NET, and so on. LabVIEW connectivity also extends to some tools like the instrument driver network that is hosted by National Instruments. So there are many third-party instrument drivers that are available. Another compelling reason to use LabVIEW is its extensive library of graphic functions for displaying and analyzing data. So you have a wide collection of graphs, some of the waveform graphs and XY graphs on the lower left, some 3D plots, and quite a feature-rich set of graphing tools in LabVIEW. Now, we've used some of these LabVIEW tools ourselves in utilities that we provide for the APx500 software. Some examples shown here are the APx polar plot utility on the upper part of this slide, and the CSD, or cumulative spectral display utility, in the lower right corner of this slide. LabVIEW also has tremendous features for processing data. So in addition to the basic numeric functions common to all programming languages, LabVIEW has powerful features for easily manipulating arrays in the array palette shown on the upper right. and an extensive library of mathematical functions. You can do almost, with LabVIEW, most of the things that you can do with MATLAB, so it's very powerful in terms of mathematical data manipulation. Next we'll talk about the structure of our LabVIEW drivers. So to begin, I'm going to start with an example that was created in C#. So this example ships with our API developer tools that are available on our website, ap.com. And this is a very simple example that configures the frequency response generator. So if you look at the code behind this little window, you'll see this area circled in the highlighted in the red box. This is a .NET constructor. It instantiates the APx500 object and initializes it. This will start the APx500 software if it's not already running, and if it is running, it will simply get a reference to it and all of its properties and methods. Now in the C# world, we have a Windows form like this that has a button. The highlighted button is called Set Generator, and there is an event handler behind this button if you look at the code. So whenever that button is clicked, this little subroutine called button frequency response 1 click is executed. And inside this try catch block, you can see the statements that are run. So let's just run through those. So first we have apx.showMeasurement. So this activates the measurement called frequency response in the signal path called signal path 1. Then we set the start frequency. So we have the command apx.frequencyresponse.generator.startFrequency.value equals, and it's set to a double. That's the value of the number typed into the start frequency box. Similarly, we set the stop frequency using a set of commands, and we set that to the value that's in the stop frequency box on the form. And finally, we set the level. And then the last statement is apx.frequencyresponse.start. That will run the measurement. So let's look at how we might run that code in LabVIEW. So in LabVIEW, LabVIEW uses a series of .NET nodes, they're called, and there are 3 basic ones. So first we have what's called a LabVIEW constructor node. This declares the APx object and connects to APx500, just like you would in C# or any other language. The next node over is called an invoke node, and it shows this little dashed arrow in the upper left corner. An invoke node essentially runs a method or a function that does something. And the third node is called a property node, and that just gets or sets the value of the property. So, so this code in LabVIEW would open a connection to the software, make active the frequency response measurement in signal path 1, and then get a reference to the frequency response measurements properties and methods. If we were to carry on down the line, we would connect this wire to the input of the next node, which gets the frequency response generator property. The output of that node goes into another property node that gets the start frequency object. Then we would go to the value property, change the value of that property to right, and we would input a value of 20 hertz here. And then we would take the reference, go to the stop frequency node, set the stop frequency just as we've done before. Carrying on down the line, we would go to the levels property, set the level of channel 1 to a certain value, in this case 100 millivolts. And finally, we have an invoke node, which will start the measurement. Now, if you run all these together, you'll see that in LabVIEW, your block diagrams get very long and narrow. So what I've done here is stretch this out. And in LabVIEW, it's considered good practice for data to flow from upper left to lower right and not to wrap back on itself. It's also good practice in LabVIEW for block diagrams to fit in exactly one screen. We tend to relax this requirement when working with .NET programming because of the nature of these very long, narrow block diagrams. So in our code, we often have the block diagram of a VI spanning, say, 2 monitors because the diagrams are so long and narrow. So this, because of this feature of .NET programming in LabVIEW, these block diagrams can be very messy in the sense that they're difficult to deal with and they span a couple of screens. Now let's look at the equivalent code using VIs from our .NET-based LabVIEW driver. So first we have a VI called open that declares the APx object and connects to it. There's an option on there to start with the software, the GUI visible or invisible. It's visible by default. Next, we create a reference to the measurement and make it active. So we're referencing frequency response measurement in signal path 1. Here we would get the current generator settings with this VI used to get the frequency response generator settings. We wire that to a bundle by name cluster element, and we just change the value of the properties that we want to change. So here we're changing the start frequency, the stop frequency, and the levels. Then we pass that back to the same VI with this bool set to true value now because we're going to set those properties, and finally we run the measurement. So just to sum up some of the features of the .NET LabVIEW driver, it does follow the NI LabVIEW driver standard. It offers you convenience and cleaner LabVIEW code. You end up with having VIs that look much more like a traditional LabVIEW block diagram than these long, thin .NET nodes. And we provide support for all of the APx sequence mode measurements in terms of configuration, running the measurements and the sequences, and handling the data. There are some limitations to the driver. It has limited support for advanced measurement settings. It also has limited support for some of the graph features, such as selecting units, points, and limits, and so on. And there is less support for bench mode than sequence mode. The reason for that fact is that, number one, bench mode first came into existence around version 4.0 of the APx software. So the LabVIEW driver predated it by quite a bit. Secondly, our thinking was that people working in bench mode are more likely going to be wanting to do R&D, and people working in LabVIEW are more likely going to be wanting to program for production test, which would be a sequence mode use case. So we decided to have more support for sequence mode. In terms of the limited support, if you've had a chance to look at our API browser, you'll note that there are tens of thousands of APIs available, and it's just not possible to provide support for everything. But you can still get at all of the advanced features. You can still use these LabVIEW.NET primitive property nodes and invoke nodes to get at all of the methods and properties that are available in the APx API. So let's look at a simple example. First, we're going to look at this example that opens an APx project file, runs the sequence, and displays the report. So if we look at the code here, it may be a little difficult to see on the screen, so I'll just run through it. We have the open VI, which opens a connection to the APx500 software. Next, we choose a project file named classdamp.approjects that's in the folder of this VI, but one level up. We call a VI to load that project file. Next, we call a utility VI that sets the report checkbox to checked so that the report will show at the end of the sequence. And then we have a VI that runs the sequence. So that's one simple example we're going to look at, and then we're going to look at a second simple example which will run the signal analyzer measurement and get the FFT data. And I'll go through that one in detail when we have the VI open. So I'll just get out of the presentation mode here, and first I'll load that example called Load Project and Run Sequence. So this VI has no controls on the front panel. I've just put a note on there to say this example has no controls or indicator. It opens an APx project file, runs the sequence, and displays the report. So if we look at its block diagram, you can see the code that I showed in the slide just a minute ago. So we have the open VI, open a project file, and then we uncheck the report and run the sequence. I'll just turn on highlight execution and I'll run this VI. You can step through it and see the flow. So first we get the reference to the APx project. We open the project file. That's what's happening here now. The report checkbox gets checked. You won't see that because it's not in view at the moment, and then we run the sequence. So it's in the middle of running the sequence, runs a few measurements, I think the big 6 or the basic 6 audio tests, and I put some limits in here to make the project fail on some of the measurements. So at the end we get the sequence report, and you can see all of the test results. So this little example illustrates just how easy it is to work with the software and with LabVIEW. You know, we have here 4 simple little VIs that we've used to open a project file, run it, and get a sequence. So you can do quite a bit with very little effort. Let's look at that next example, which was to run the FFT measurement and get the data. So I'll just bring up the block diagram here, and this is a little bit hard to see. So I'll go back to the presentation mode and just walk through that with you. So we have the open APx500 VI that opens the connection to the software. We form what's called the signal path and measurement object. So this is a cluster that we use to tell the sequencer what measurement we want to work with. In this case, it's set to signal path 1 and the signal analyzer measurement. We then run the measurement. Next, we call this utility VI that gets XY plots, and we tell it that from the signal analyzer measurement, we want to get the FFT spectrum plot, and then we pass that data to a graph indicator and another to a cluster indicator that shows us the units. So let's go through and run that little example so you can see the front panel is blank to begin with. We'll just run the VI. So it will tell the software to go to the signal analyzer measurement, run the measurement, and get back the data. You'll notice here that it's a little bit hard to see, but I have 863 FFT points. So really I just wanted to demonstrate how easy it is to run a measurement and get back the data using LabVIEW. Okay, we'll step back into presentation mode here. So in the previous example I pointed out the signal path and measurement cluster, and this is a cluster that we use to index specific measurements in the sequencer. So you'll notice that the cluster has a signal path name, so there would be one for every signal path. And then there's an array of clusters of measurements, and each element in the array contains the name of the measurement, whether or not it's checked, and the measurement type. So this index here is an index into the array, this array of clusters, and this tells us that we want to use element number 7 of the array, which in our case would be the signal analyzer measurement. Now you've probably noticed that these controls are quite a garish or ugly orange color, and that's been done in this case to denote that these are what are called type defs. A type def is a special type of control in LabVIEW that makes it very convenient to manage your code. So if you have used a custom control in a number of places in your driver or your VI collection, if they are a type def control and you want to change the nature of that control, for example, let's say you have a cluster control that has 10 elements in it and you want to add another element, If it's a type-def control, you can add that element to the type-def and it will propagate all the way through your VI collection. So it's very convenient in terms of managing the code. So an example of how this signal path and measurement cluster is used, we pass in this cluster control called signal path and measurement. It goes into the measurement and it's passed out the other side just for convenience because we use it a lot in the VI collection that's in the .NET driver. Another very important point I wanted to make is that the APx.NET LabVIEW driver runs the measurement using what's called the sequencer. And this is an important point. So first of all, you'll notice that in the APx software there are some measurements that have a generator on button as opposed to a start button. And usually, or almost always, well, virtually always, those measurements have results that are being updated continuously, live. So, you know, it would be possible to just pull the data off that graph from the live display, but doing so would not give you settled measurements. Now, when you run the measurement from the sequencer, either by clicking on this play button in the sequencer, or by right-clicking on the measurement and selecting Start Selected Measurement, the measurement will be run from the sequencer. What that does is two important things. Well, actually three important things. It will run any sequence steps that are part of that measurement. Secondly, it will run the measurement, get settled readings, accumulate them in the sequence data collection. And thirdly, it will check any results, check the results against any limits that you have put on the result. So getting the data into this sequence measurement collection is a way to ensure that you have settled readings. And that's the method that we've used within the VIs in the LabVIEW driver. Now I wanted to just give you a caution in that sense. So you'll notice earlier in the example that we got the FFT points that I pointed out the number of points returned. And I have that highlighted on the screen here. So this FFT probably had an FFT length of 16 K-samples. In other words, the acquisition would be 16,384 samples, and the number of points on the FFT is half of that, or 8,192. But you'll notice that the number of points returned from the sequence collection is only 686. And the consequence of that is the sequence collection only contains the number of points required to render the graphs that are put into the report. So I wanted to point that out because quite often users want to work with the FFT and do some calculations, such as deriving the THD ratio or calculating the RMS level within a certain frequency range. And to accurately work with the FFT data, you need to get all of the points from the FFT. So we've provided a special measurement here that will run the signal analyzer and get back all of the points in the FFT. That's available in the Action Status menu. And I can just demonstrate that quickly. I think I have a little example here. So this one's called Run FFT Measurement and Get All Points. Seems like it's open off screen somewhere. Let me try closing it. Oh, I see. Okay. Pardon me. It was way over here out of the window range. So this is the example. Let's just have a look at the code. So here we have the APx open VI that gets the reference to APx or opens the software. We form the signal analyzer. This one is a little bit different. We pass in the name of the signal path and the name of the measurement, which would be on the front panel here, signal path 1 and signal analyzer. We just run this signal analyzer measurement. There's a little Boolean connected here that the function of it is run first. So if set to true, it'll run the measurement first. Otherwise, it'll just get back the data. And it returns a cluster here of frequency and levels, and then we can plot that on the graph. So let's run this VI and see, we had something like either 600 or 800 points the previous time. Now if we run it, we have the FFT length is 16K, and you'll notice that the number of FFT points returned is 8,193. So there's 8192 plus 1 point for the DC bin. Similarly, if I quickly change this to, say, 32K and run the example again, number of points should be doubled, and we get back 16,385. Again, 1 point for the DC bin. So just another thing that I wanted to point out, to be careful when you're working with the FFT results, that you want to get back all of the points, and there are ways to do that get you all the points. Okay, so let's look at the driver menu palette. So the menu palette is stored where any instrument driver menu palette would be. So from the main function palette, you would choose instrument I/O, then instrument drivers, and you'll see listed here APx500. There's a version number on there. The one in the slide is a couple of revisions out of date, but the 4.41 would look the same. And here you can see the main menu palette of the APx500 .NET driver collection. Now the VIs are organized according to the recommendations in the LabVIEW plug-and-play instrument driver guidelines. So the recommended driver structure is shown in the top on this graphic, and you can see the menu palette for the driver on the bottom. So we have the initialize VI, which opens the connection to the instrument, the close VI, which closes it, and then we have the basic groupings. So the configuration VIs configure the instrument to perform specific operations. The action status VIs cause the instrument to perform test and measurement operations. The data VIs transfer data to or from the instrument, and the utility VIs perform a variety of auxiliary operations. The APx.NET driver also has some special menu palettes for signal path setup, configuration, and for bench mode. These are shown over here, signal path setup and bench mode, because those are very important sections in the APx software. Also should point out that the VI icons are color-coded, so the ones with the blue bar at the top, the blue bar denotes that they are for sequence mode only. The VIs with the green bar at the top denote that they are for bench mode only, and the VIs that have both blue and a green, a mixture of blue and green bar at the top, denote that they are either dual mode, they work in both modes, or they are polymorphic. Next, we have the VI tree. So the VI tree is found on the top menu palette of the driver. This VI is not intended to run, but rather it illustrates the main VIs in the driver collection. The main VIs are located on its block diagram, and they're grouped according to function. All right, so let's look at some of the measurements that are available in the .NET driver, how to configure measurements. So inside the VI tree, this is a bit of a zoomed-in view, and you can see there's a row for every measurement in sequence mode. So we have them arranged alphabetically: acoustic response, bandpass frequency sweep, bandpass level sweep, and so on. And you'll notice that most of the measurements have 3 VIs in the collection to configure the measurement. And there's a certain paradigm to that. So for example, this is the signal analyzer collection, or the menu palette for configuring the signal analyzer measurement. There's one to get or set the properties of the analyzer, another one to get or set the properties of the generator, and a third one that is really just a combination of the first 2. That'll get or set the properties of the analyzer and or the generator. So we can look at the measurement configuration in the context of the APx software. In the control panel here, we have a generator group, which has all the controls needed to configure the generator, such as the waveform, the levels, the frequency, and so on. And the analog of that in the driver is the configuration VI. So we have the main VI named APx500 config signal analyzer get set generator. Similarly, for the analyzer, which was formerly called acquisition and analysis, we have a special VI to configure to get or set the properties of the acquisition and analysis, such as the FFT length, the window used, and so on. Now, if you dig into these VIs, you'll see a great big cluster of orange-colored controls, again denoting that these are type-def controls. And there's a large number of controls that essentially match the controls that are available in the GUI, the graphical user interface. However, you'll notice that there are many more controls in the cluster than are available on the screen at any one time. And the reason for that is, depending on the mode that you're in the APx500 software, any of the controls that are not necessary for that use case or that context are going to be hidden or invisible. Whereas in the LabVIEW driver, they all have to be present because the driver has to work for whatever mode you're in. So for example, here I'm showing, obviously I'm in an analog output mode, and I can configure the level of the generator in volts RMS. So I don't need to show units such as digital units or whether the waveform is bit exact. But over in the cluster used to control the generator, it needs to work for digital as well as analog, so all of those controls are available. So you will see many more controls in the VI configuration cluster than you do see in the graphical user interface of the APx500 software at any one time. This shows the acquisition and analysis section, or the analyzer section of the APx500 GUI, and you can see the corresponding cluster of controls in the .NET driver. You can see a lot of similar controls. So we have the acquisition length type here, and the acquisition length both set to auto, and so on. So again, there are more controls in the VI cluster than are visible on the screen within the software at any one time. Now these get set VIs are all used in a similar fashion. Typically what we do is we call the get set VI with the Boolean the Boolean is named set, and it is set to false by default. So we call it with the set Boolean set to false to get the current generator settings. Then we wire this to a bundle by name cluster, and we change the desired setting. And finally, we call that get set configuration VI again, but this time with the set Boolean equal to true, and that causes the value to change. Now the reason for doing that is if we were to simply call the set VI and wire some value in there, you might choose a value that's not appropriate for the current configuration. For example, you might try to set the level of the generator in volts RMS, and at the current time that you do that, the generator is actually configured for digital, and it'll throw an error. So this is essentially the paradigm that we follow all the way throughout the driver package. Again, you would get the current settings, bundle by name, and change the ones that you want, and then call that get set VI with the set bool set to true. So let's look at some examples of configuring the measurements. So first we'll use the get set generator and get set acquisition and analysis VIs, and then we'll use the get set all VIs. I'm going to cancel out of the presentation mode here and load those examples. So the first example is configure it's off the screen again, pardon me. Set this up on a larger monitor originally. Okay, so this example is called Configure Signal Analyzer Generator and Analysis VI. So let's look at the block diagram here. So it's a little bit more complicated, but still pretty simple. So we have a little loop here that's executed 2 times, and the loop counter is wired to the this case structure. So we do the case 0 first, and then case 1 second. So first we open a connection to the instrument. We form the signal path and measurement cluster just like we did before. We go into the loop and run the first case. So we get the signal analyzer generator settings here with this set bool equal to false. We bundle by name, and here we change the properties that we want to change. So the waveform selected index of 2 corresponds to, these are 0-based indices, so this corresponds to selecting sine dual in the software. Then we go about setting a bunch of properties, changing a bunch of properties that we want. So we have the frequency A, frequency B, the dual channel assignments, the levels of A and B, the type of dual sign that we're generating, and whether or not the levels track channel 1. Then we'll execute the second case. So in the second case, we get the signal acquisition and analysis settings, again with this bool set to false. We bundle by name to change the ones that we want, in this case the FFT length and the number of averages. We then call the getSetVI with the Boolean set to true. Finally, we step out of the loop, we run the measurement, then we get the XY plots from that measurement collection, and we choose the FFT spectrum and plot it on the graph. So let's go ahead and run this little VI and see how it goes. So I'll run it, and it's switched over to sine dual, it's done a measurement, and then I get back the data. So again, you can see, pretty simple. I've only used maybe 6 or 7 VIs here, and I was able to control the generator and the acquisition settings. Let's quickly have a look at the same VI, but this time we'll use the getSetAll. So probably off screen here again. Here it is. No. All right, so it looks pretty much the same on the front panel. Let's look at the block diagram here. So here we, again, open a connection to APx. We form the signal path and measurement cluster. So this time we call the getSetAll. The getSetAll with the set Boolean equal false. Here we bundle by name, and we change the properties that we want. So we have properties here to change both the generator properties and the signal acquisition and analysis properties. We only need 1 case in this example. Then we run the measurement, get back the data, and plot it on a graph. So let's go ahead and run that quickly. So we're switching back to sine, single frequency, and we get a result back here. Incidentally, for this example, I'm connected to I forgot to mention this, but I'm connected to a Class D amplifier with 2 channels that has a couple of load resistors connected. All right, so let's go back to presentation mode here. Just one more thing I wanted to point out. So we went through these 2 examples. So there's a special VI in the utility collection called the APx Simple Error Handling VI. And I'm going to show this in a minute, but LabVIEW is very clunky in terms of handling .NET errors. So almost any error in LabVIEW, any .NET error results in an error code 1172 with a very cryptic error message that's not very helpful. So what this error handler does is it traps any errors with code 1172, and then it calls a VI or calls an API from the APx500 that gives it the last error that occurred in APx, and it gives you an error message that is much more easy to interpret. So let's have a look at that quickly. So I have an example here called example error handler. I'm going to bring that up. And on the front panel, what this example does, it tries to set the, for the signal analyzer measurement in signal path 1, it tries to set the frequency to 500 kilohertz. So that's beyond the capability of the analyzer. It's going to throw an error. And I have a little selector here, which can choose LabVIEW Error Handler or APx Error Handler. So let me just leave it at LabVIEW Error Handler, and we'll see what happens. So I get LabVIEW's error message, and it might be a little hard to read, so I'll read some of it for you here. It says, error 1172 occurred at property node arg2 system IO file not found exception, could not load file or assembly. Audio precision app services version 4.4.0.52, culture equals neutral, public key token, blah, blah, blah. So as you can see, you get this standard 1172 error message, and the message is not very helpful. It's very complicated. So let's flip over instead to the APx error handler, and just to show you on the screen what happens here, on the block diagram. So this is the function that gets the properties. Here we set them to that frequency of 500K, and then this little error handling enum is wired to this case. So in the case of the APx error handler, we call that error handler. And let's have a look when we run it here. So this time we get an error message that says, error 7123 occurred at example error handling VI. Possible reasons. The value 500 kilohertz is out of range. Allowed values are between 5 hertz and 204.5 kilohertz. So a much nicer error message and much more easy to interpret. So if you want to, you're welcome to go and look at that error handler VI. Again, that's going to be off screen. But if I drag it over here, we can see the block diagram. And basically, it unbundles the error code. If it's equal to 1172, it goes into this case which calls this last exception API and gets a nice, meaningful error message from the APx500 API. All right, so back to the presentation.